In this video, we're going to look at a different technique to see the relationships between pressure, specific volume, let's say, and temperature of gases, and how can we basically relate the three of them through something called a generalized compressibility chart. Before I start to show you how the generalized compressibility chart looks like, there's a few variables or constants that we need to look at and analyze. And one of them is going to be, let's say, if I start off the discussion by showing you a gas that is confined in this piston cylinder arrangement, and what I say is that this entire system is held at a constant temperature. So let's say the temperature in here is T1. Okay, and now this piston can be moved in a way. Let's say I'm only changing the pressure of this gas within the system, so the pressure can be decreased, the pressure can be increased, but the system is such that the temperature remains constant. And then let's say I have another system of, let's say, the same gas, and this one is at a different temperature, so I'm holding temperature constant again, so this is going to be T2, let's say. And again, the only thing that I'm changing over here is pressure. So I'm changing only pressure, increasing it or decreasing it. I'm holding the temperatures constant. And then I'm not only measuring, let's suppose that I'm not only measuring the pressure at each instant um, for both of these systems, but also I'm looking at the specific volume. So now, uh, when I've measured pressure and I've measured the specific volume as well, and I know what the temperature is because I'm holding the temperature constant. So that means I could have a ratio, I could work out a ratio that could be of the form, let's say, PV uh, divided by T, or I could, instead of using specific volume over here, I could use something called V dash, and V dash is basically volume per mole. Okay, so it's just in terms of the molar basis. So volume per mole is defined and denoted by V dash. So I could um, work out this ratio, right? I know all three values. That means I could find out this ratio. And now I'm saying that the only thing that I'm changing is I'm increasing or decreasing the pressure. So let me put that on this x-axis. It's increasing in this direction, decreasing in the other one. So let's say for this system, let's assume that there's a certain trend that the system is going to follow. And let's say I'm decreasing the pressure, so that trend is going to be something uh, like this. And for the second one, so this is when our system is at T1, it's for the same gas. Both systems have the same gas. The second system is going to have, let's say, another kind of trend because now the temperature is different over here. So T2 is going to be different, but it's going to show us the same trend. And now if I had, let's say, another system that would be at a different temperature, it would be at T3, let's say, and so on and so forth. There can be so many of these. But what's interesting is that if I extrapolate now uh, this trend towards finding out what the trend is going to look like, what this ratio is going to look like when I approach a pressure of 0, then I can apply the limit and extrapolate it basically, and I would reach this point. Let me just close this. I'm going to reach this point, and it's going to be one particular point. All of these are going to come to this point. They're going to converge on this point. And this point has been experimentally determined. It's called the universal gas constant. It's represented by R dash. So basically, a ratio of PV dash divided by time when we basically approach the limit where pressure is approaching 0, that is equal to the universal gas constant. Okay, so do you see how we come up with this value for the universal gas constant? And the universal gas constant R dash denotes basically the common limit for all temperatures over here. And if I was to repeat this procedure for other gases, it would be found that in every instance, as I apply this limit here to this ratio with pressure approaching 0 at fixed temperatures, it gives me the same value, which is R dash. That is why this is called the universal gas constant, because it is applicable for all gases. So usually what we see is that the universal gas constant's value is given in terms of, let's say, different systems, different unit systems. We are going to be concerned with the SI unit systems in this video, so we're just going to look at that. So now that I have the value of the universal gas constant, I can see that the universal gas constant is being related to pressure, volume, and temperature altogether. I could move on and define something called the compressibility factor. And compressibility factor is denoted by the symbol Z, and it's just a notation to indicate, let's say, PV dash over RT. This is a dimensionless quantity, dimensionless ratio. R dash, universal gas constant, is represented with R dash. So there's a dash on top if I missed that before. Universal gas constant is represented by R dash. Okay, so Z is given in terms of specific volume on a molar basis, universal gas constant that is applicable for all gases. And this dimensionless ratio, and what do I mean when I say dimensionless? It means that there are no dimensions of this compressibility factors. There's no units for it. All of them cancel out with each other, and it's a dimensionless quantity. So now that I have this Z as a unitless value, and I can define, let's say, V dash is, if I want to relate it to specific volume, then I could write it in terms of M into V, where M is going to be the molecular weight of whatever the gas is that we're looking at. And basically I could write Z in terms of, let's say if I substitute this in here, and R dash, if I specified, let's say if I'm looking at the specific gas, then I could write the value for R. That is going to be equal to the universal gas constant divided by the molecular mass. So if I substitute both of these in here, then I could write Z in terms of just PV by RT now. Okay. So yeah, and R is, like I said, it's a constant for the particular gas that we're looking at. Obviously, it will change depending on the molecular weight here, and molecular weight changes for every gas that we're looking at. And now what I can do is, if let's say I was to look at that same relationship that I was looking at before, which was limiting when pressure approaches 0, and I said that it was going to be equal to PV dash by T equals R dash. If I basically um, look at this in terms of the z over here now, I could write this limit, let's say, uh, for the compressibility factor now, which would be with pressure approaching 0, the compressibility factor is going to be approaching 1. Okay. Yeah, because obviously we're going to be taking this onto the other side. So there's going to be 1. We're going to be left with 1 on the right hand side, and this is the limit that we're going to get, that as the pressure approaches 0, compressibility factor approaches 1. So if we have to, let's say, verify this, we could just look at, let's say, this diagram over here, which represents basically the variation of the compressibility factor for hydrogen. We're just looking at hydrogen over here. For different temperatures now, different constant temperatures, these are different constant temperature lines. What we see is that as we move towards the left-hand side on this graph, the compressibility factor value reaches 1 as the pressure becomes 0 over here. Okay. So this is just a chart that gives us the compressibility factor for hydrogen versus pressure at different specified temperatures over here. And now similar charts like this have been prepared for other gases as well, different gases. And when we look at all these charts together, what is found out is that qualitatively, or like when you're looking at it just by observing these graphs, what you see is that they look kind of similar. They're qualitatively similar. And when you study it further, what you see is that if you change this x-axis here, and you plot, let's say, this y-axis for something else over here, some other variable on the x-axis, what you see is that even the way this graph changes quantitatively for different gases is similar to, and this is this entire thing about all of these gases being qualitatively similar and quantitatively similar is called the principle of corresponding states. And one of the ways to do this is to change the variable on the x-axis is that we basically look at the compressibility factor z on the y-axis versus let's say a dimensionless reduced pressure on the x-axis. So it's called PR. It's called reduced pressure. It's P and this is R over here. And reduced pressure is just basically a dimensionless quantity. It's just a ratio of pressure. So it's a ratio of the given pressure, let's say, to the critical pressure for that gas. Okay, so this is how you plot the two, and then you can also, because we also need to now somehow account for the constant temperatures here. So what you do is that you go with something called reduced temperature here. So we've got reduced pressure here, P, and the subscript is capital R. And we've got reduced temperature here, and temperature is equal to, reduced temperature is equal to the given temperature divided by the critical temperature for that gas. So now we could, let's say, let me move on here and show you how it's going to look like. So we've got compressibility factor Z on the y-axis, and we've got reduced pressure on the x-axis, which is not actually a pressure. It's a dimensionless quantity. It's not a pressure. Just make sure that you spot that here. And then we've got different constant reduced temperature lines here, and these are not temperatures. Again, these are dimensionless quantities. So now you've got so many different gases here, and they give you a generalized form that can be used. So what you see is that all of these curves are accounting for so many different kinds of gases. And well, when you look at the compressibility charts, the generalized compressibility charts, they account for about 30 gases that are used to develop the charts. And a better way to look at these charts is if you're, let's say, using Shapiro's book, go to the end of the book and look at figures A1, A2, and A3. And these three figures in the appendices are going to give you a better representation of how you can relate the three quantities here. I'm just going to show you the figure A1 here. And in the figure A1, what you will see is that the reduced pressure varies from 0 until 1, and that is the range over here. Then in figure A2, you will see that it varies from 0 until 10, and in A3 you will see that it varies from 10 until 40, and that is just for ease and simplicity of use, because we have to basically expand this and zoom in and see what it looks like. That is why we're looking at 0 until 1. Otherwise we could have just looked at 0 until 40 all the way, but then we wouldn't be able to zoom in here. So this is these charts, A1, A2, and A3, they've been developed by using basically 30 gases and accounting for all of them. And the error percentage is really low, less than 5%, let's say. So what you will see is that, okay, you've got Z on the y-axis, you've got reduced pressure on the x-axis, then you've got these lines that represent reduced temperature, TR, but then you've got another dotted line here as well that is called pseudo-reduced specific volume. Okay, so you can work out specific volume as well from the table. So this is called pseudo-reduced specific volume, and this is equal to V dash divided by R dash, which is the universal gas constant, into critical temperature divided by critical pressure. So this is called the pseudo-reduced specific volume. We don't work with the reduced specific volume. You could say that, why are we not working with reduced specific volume? It's just that it's found out that it's easier to basically graph the pseudo-reduced volume onto this figure here. That is why we do this. You'll see these lines. These are the pseudo-reduced volume lines. And so what is the point of basically looking at this generalized compressibility charts? I mean, we've already studied, or we've already looked at the steam tables or the PVT surfaces. So this is not a substitute for those. This is not a substitute for PVT data in the form of tables. That is much more accurate. It's just that this gives us a chance to work things in a simpler way. It's accurate, it's simpler. All you have to do is you just have to work out reduced pressure, reduced volume, just look at the table, find out where it is, find out the compressibility factor, work out, let's say, the specific volume or whatever you need to work out. So that is the only reason. This chart shouldn't be used. Let me emphasize this point. You should not use this chart if you have steam table data available. If you have PVT data available in the form of a table or in the form of a computer software, just use it if you're trying to find estimates if you do not have more accurate data available. Okay, so I'm just going to go on and show you the second chart, which is A2. This is chart A2. And again, you have reduced pressure on the x-axis, compressibility factor on the y-axis. You've got values for TR over here. These graphs. These lines represent TR, which is reduced temperature, and these dotted lines represent pseudo-reduced volume. Okay, we R dash. And just like this, you will also have A3, which is going to give you now reduced pressure on the x-axis from 10 until 40, and compressibility factor on the y-axis. Again, you've got TR, and you've got TR as the lines, and you've got pseudo-reduced volume VR dash as the dotted lines. So I'm just going to go on and show you an example. Let's say we've got a tank that is filled with water vapor. You've got the initial pressure, initial temperature, and it's being cooled. So heat is being extracted out of it until the temperature has lowered down to 400 degrees Celsius. And you have to use the compressibility chart to find out not only the specific volume of the water vapor, but also the pressure at the final state. And then I'm going to leave this part for you to do yourself. So you have to compare the values that you find here to the values that you would obtain for the same problem if you did this problem by using the superheated vapor table. So for this, what I would have to do is now, I would need to find out, first of all, let's say at the initial state, I would need to find out the reduced temperature. So I'm going to call that TR1, and that is equal to T1 divided by TC at 1, which is the critical temperature at 1. So where am I going to find this out from? You can go to table A1, and over there for water vapors, let's say, you can find out what is the value for TC. It comes out to be around, let's say, 647 kelvins. And if you divided T1, which is 520 degrees, or if I was doing it in kelvins, it would be 793 kelvins. And I just divide this by 647 kelvins, and this is going to give me the value for the reduced temperature, which is going to be 1.23. And now the same way, I'm going to find out the value for PR1, which is the reduced pressure at state 1, and that is going to be equal to the pressure that is given to me, which is 20 megapascals divided by critical pressure at this initial state, which is state 1. So again, I'm going to go to table A1, and I'm going to find out, I'm going to look at the table and I'm going to find out the value for this over here, and it's going to be equal to 22.09. I'm just going to divide 20 megapascals by 22.09, and it's going to give me the value for PR1, which is going to be 0.91. Now that I've got these values, what I can do is I can look at this chart here, and let's say, because I'm looking at reduced pressure, so it's going to be 0.91, let's say it's somewhere here, and I said that my reduced temperature value is 1.23, so I move on this chart and I see that this is 1.2, so it should be somewhere here. I'm going to draw a vertical from here. Let's say, let's hope I do a good job at drawing this vertical. Okay, so let's say this is the point where I've got this curve of TR equals 1.23. And now I'm just going to draw a horizontal from here until, let's say, here. And this is going to give me the value for the compressibility factor. So let's say 0.83 or something like that. So I've got the compressibility factor, which is 0.83. And now what I can do is the equation for a compressibility factor, which was Z equals in the form of PV and RT, I can just, because the only variable that is unknown now from that equation is the specific volume, so I can just write it in terms of specific volume, which is going to be equal to Z1 into RT1 divided by P1. Or what I could do is I could write this in terms of the universal gas constant, so that's going to be equal to Z1 into, because this is going to be equal to R dash by M, so I'm just going to substitute that here, R dash into T1 by M into P1. So the molecular mass, I can also find this out in table A1, or I could just work it out in my head because it's water, so it's H2O. And the molecular mass is going to be, if I'm not looking to be too accurate, it's going to be 2 into 1. I think this is going to be 1.008, but I'm just going to assume it's 1 plus, because I've got only one oxygen here, so it's going to be 1 into 16. So the molecular weight is going to be somewhere around 18. 18 what? It's going to be 18 kilogram per moles. Kilogram per kilomole. So I'm just going to substitute this value, Z1, from here. I know what this value is. This is given to me. It's 520 degrees centigrade, but to keep the units consistent, I'm going to write it in terms of kelvins, which is 793 kelvins. The pressure, I'm going to write in terms of pascals, let's say. So 20 into 10 to the power 6. And I've got R dash, which is going to be 8314 Newton meters per kilomoles into Kelvin. So yeah, I've got everything given now, and I can work out the value for V1. You can do this yourself, see if the units are consistent or not. I'm just going to tell you what V1 is going to be equal to be. It's going to be 0.015 meter cube per kilogram. Okay, so what you can do now is you can go ahead and find out the pressure at state 2 yourself, part B, and you can compare the two as well.